All right, so things look good as far as combinations and permutations. I graded one question from each of the 4 sections. So the shirt question, I think everybody got right. So 4 sizes, 6 colors, and 3 emblem choices. And so that's a straight product rule, right? The task of designing a shirt is picking the size and then the color and then the emblem. And so you multiply the number of ways to do each task, and you get 72 ways to do the whole thing. Section 2, I picked out question 1, which was the number of ways you can assign 3 different prizes if you sell 1,000 tickets. And the key word there is different prizes. So if the prizes differ from one another, the order in which you assign these makes a difference, right? Not the order of the assignment, but the designation of which ticket gets which prize, right? So you're not just picking 3 prizes out of 1,000, which would be a straight product rule. It's actually 3 prizes where the order matters. And so that's 1,000 times 999 times 998, right? So it's 1,000 over 3, or this thing. If the order doesn't matter, then that's a combination. So you divide out by the number of ways you can arrange those 3 selections. So it gets divided by an extra 6. And then question 3, I went ahead and did number 18. So this was the inclusion-exclusion principle. And then section 4, I did number 3, which was the total number of subsets. So it looked like pretty much people were comfortable with what was going on with these. If you've got questions about them, please go ahead and ask, because there'll definitely be combinations, permutations on the final. The final will be more of the stuff we've done since the midterm, but it will definitely have a lot of proofs on the exam as well. I am not going to ask you about languages and grammars and Turing machines and state machines on the final, okay, because we haven't had a homework on those. So we'll keep talking about those today, and we'll finish up that set of topics, but those will not be on the exam, okay? So it's everything up through that point, but not including that stuff. So you can relax on this material. So finishing up on this idea of BNF, I mentioned some coding that I had to work with BNF. I just want to kind of show you this. This is a sample BNF for an expression. So we're trying to parse an arithmetic expression containing variables or numbers, and including parentheses. So variables can be, a succession of letters or digits, as long as it begins with a letter. So num is just a plain old number, right? It's either a digit followed by a num, or it's just a digit. And digit is just 0 through 9. So a num could be a single digit, or it could be a digit followed by another num, which could be a digit. So it could be 2 digits or 3 digits or any number of digits. A variable is an alpha, that's a letter followed by a variable, or it's just an alpha. So I guess variables are just letters. Operators are plus, minus, times, or divide. An expression is an L expression, an operator, and an expression, or it's just an L expression, or it's a minus followed by an expression. And an L expression can be a variable, a number, or an expression in parentheses. And these aren't necessarily obvious why these make sense, but if you start working through these things and think about an expression like a plus b times C plus D. So let me just jot these down. I'm just going to do the first two.
So in C language, that parse H is in quotes because that's one you wrote yourself?
Yeah, that's in my current directory.
Okay.
Yeah.
And it's, to me, it's kind of like, I'm kind of related to other things I've learned in this term.
Mhm.
And it seems to me like B and F, those 5 lines up there, is kind of like function protocols.
A little bit, yeah.
I mean, what you're trying to do, it's not the same thing, but what you're trying to do is set out all possible ways something can occur.
Yeah, basically.
Is that correct?
That's not exactly what function protocols do,
No,
but
no,
yeah,
I
that's
understand,
that's a good view of BNF, yeah.
Okay.
So variable is just a variable, num is just a number, op is just plus, minus, times, or divide. So the more interesting parts are expression and L expression. And suppose you're faced with a string like this, and you want to know, is this an expression? Well, we can ask, is it an L expression followed by an operator followed by a number? Or is it just an L expression, or is it a minus sign followed by an expression? If it's any of those, then yes, it is an expression. Okay. Well, there's no minus sign in the beginning, so we know it's not a minus sign followed by an expression. If it's an L expression, it either has to be a variable, well, variables don't start with parentheses, or a number, it's not a number, or a parentheses followed by an expression followed by a parentheses. Okay, if it's a parentheses, expression, parentheses, then there's our parentheses, A plus B, close paren, times C plus D, would have to be an expression, and then we've got our closing parentheses. And if we try to parse this as an expression, we'll find it's not an expression. So this thing is not an L expression, it's not a minus sign expression, but it may be an L expression, an operator, and this should be expression. Yeah, this is expression here. Well, if we diagram this, this will turn out to be an L expression. This will be an operator, and this whole thing will be an expression. Okay, why is this an L expression? Because it's a parentheses followed by an expression, A plus B, followed by a close paren. Why is A plus B an expression? Because an expression is an L expression, an operator, and an expression. Well, that A is a variable, so that's an L expression. The plus is an operator. The B is a variable, so that's an L expression. So this is an L expression, an operator, and B itself is actually an expression, because an expression can be an L expression, which is a variable. So this whole thing is an L expression, and this is an operator, and C plus D in parentheses. Again, that's an expression because an expression can be an L expression, which is a parentheses followed by an expression. And why is C plus D an expression? Because it's an L expression, it's a L expression followed by an operator followed by an expression. C is an L expression because an L expression can be a variable, plus is an operator because that's what an operator is, and D is an expression because an expression can be an L expression, which is a variable. So if we can diagram this sentence, right, using these rules, this BNF, this description of the language, and we can get all the way to the end of that sentence and say, yes, it is an EXP, right, then we've successfully parsed this and said that's an expression. And that's hard for us to do on paper because we've got so many choices, right? We kind of cheated because I knew how this was going to parse out, but theoretically you have to try this followed by that, and if that doesn't work, you have to try this, and if that doesn't work, you have to try a minus followed by that. And it's recursive, right? An expression can be an L expression, which can be a parentheses expression parentheses. So you got to keep track of all this stuff, right? And that's hard for people, really easy for computers. And so this parse.h is a package that I wrote a while ago, and it lets me basically take this kind of description, this BNF form, and write it as a series of C statements. So my whole thing is called parse, and I want to know if I have an expression, so I can say stran expression. And if I find an expression, then I'm going to go to state S1, and state S1, I'm going to say, am I at the end of my string? And if I am, I'll say success. So there's an implicit end of string that I want to match at the end of this expression versus an expression with some trailing stuff. And then the description of an expression is a minus sign, which takes me to state S4, followed by an expression, which registers success. So a minus sign followed by an expression, that's an expression. If I don't find that minus sign, I can look for an L expression, go to state S5, look for an operator, go to state S6, look for an expression. So an L expression, operator expression will register success. And if it doesn't match that, if it's an L expression and I go to S5 and it didn't match an operator, I can match lambda, the empty string. I can say, well, since I matched an L expression, I'm going to call that success also. And so that matches this notion that an expression is just an L expression. So you stay up late enough at night and eat enough Chinese food, and you start to think in these terms, okay? And taking this BNF and translating it into all of this becomes very straightforward, or at least it did for me. And once I've written that, my main program is trivial. Right, I basically read a line from standard in, I get rid of the null terminator at the end, and then I just say parse. And if it returns an error, then I say there's a problem, and this variable max string will tell me where the problem occurred. So I just space over that many spots, and I print out a little caret with a question mark. And so if I compile this and run it and ignore the warnings, like I said, I wrote this a while ago, I can do a plus b times c plus d, and that's a good expression. But a plus b plus times c plus d, and it'll tell me there's a problem right there. That's where the BNF failed to match the input. Right? Or the C number sign, ha didn't match what I was expecting for a variable there. And while you're doing this kind of parsing, you can be saving the information along the way, so that when you're done, you not only know this is a valid expression, you can actually be evaluating what it's equal to, or create a set of code that would, when you run it, perform this calculation. And that's written on top of this parse package. Okay, so I outed myself, 1985, and it's just a bunch of preprocessor definitions. So you can run this through a standard C compiler, but it's really doing symbolic manipulation. But buried in all of this gibberish is the stuff you need to be able to just write a BNF and run it. And like I say, after a few months of doing this, you start to see the world like this, and it all makes perfect sense. For lots of late nights and things like that. So this stuff that we've been talking about, languages and grammars and so on, very applicable to computer science, right? This is how We do syntax checking and compilation, converting things from one language into another, for example, from C into assembly language, or assembly language into machine code. And there's lots of tools out there that will do this kind of thing. So, do I not have Lex? Oh, boo. Well, Lex and Yak. Lex is the lexical analyzer. Yak stands for yet another compiler. And it's a program that lets you write a description of a compiler and then compile that description into an actual compiler. And this happens a lot, and so this was yet another compiler. And I don't think they're installed by default anymore. But Lex, Yak, other tools like that.
So you're saying writing the BNF directly, at least for you, made the writing of the C code easier, and it told you what and how to write the C code.
Yeah. So this was my real challenge at this point in my life, was writing BNF, right? Thinking about how you can describe a language in terms of these sorts of rules for what constitutes a member of that language, a sentence or an assignment statement or whatever. And then once you have that BNF written, it's mechanical to write all of this other stuff. It's a weird little procedure, but it's very straightforward. And there's a more complex BNF. This was for a stack-based machine I was designing and writing a language for. And it's a longer BNF, and so this code is longer, but it's exactly the same process of writing it. And then the main program is pretty much always the same.
So I wondered what the word parse meant. I've heard it a lot. And so basically, this is what it means, writing the BNF.
So parse, to me, when I use the word parse, I'm talking about trying to interpret something, trying to interpret the structure of something. So parsing an expression is looking at the expression and figuring out, this thing gets multiplied by that thing and then added to this other thing. And this first thing is a variable, and the second thing is an array, and the index is this, and this other thing is an expression that's in parentheses and is calling a trig function.
But it's got to fit some pattern.
It's got to fit some pattern.
That's already established.
Right. And so you have something, it might be a BNF, it might be something much less explicit.
Okay.
For example, a lot of the stuff we'll do in 222, you'll write a program that you can interact with through the command line, and you'll say things like insert the number 5, or delete the number 7, or search for the number 3, or print everything that I've inserted into this structure. And so you type in these one-line commands, and it might be an I followed by an integer, or a D followed by an integer, or an S, or maybe just a P. Or you might have a command like insert 5 through 8. And if you see an I followed by a space, followed by a number, a dash, and a number, it means you should insert all the numbers between here and here into your structure, right? So the process of taking this line of input and figuring out what are you asking to do here, that's what I would call parsing. All right, so it's interpreting in some sense.
What course would you learn BNF more in?
Like a language course, a compiler course.
Maybe Washington.
No, I mean I sometimes mention it in 215, sometimes not. I did this quarter. But it's not really anything we would go over.
Here at Clark?
Yeah.
Okay.
Compiler design is more of like a third, fourth year subject, or maybe a graduate school.
But still, it seems pretty.
Automata theory might go into some of it. And automata theory is a third year course at WSU, I believe.
But still, it seems like pretty interesting stuff.
I think it's really interesting stuff. And like I say, this was one of my big hammers when I was an undergrad, right? Because the assembly language of our system came with a bunch of libraries, and one of the libraries let you do these kinds of state transitions, and that's all I did. I wrote a version of C that basically mimicked what you could do with their assembly language library. But then, I just started seeing the world as things that needed to be parsed. And I started writing BNF for this and that and the other thing. I managed to use it for lots of different situations.
You mean you were parsing your meals and?
Yeah, totally. Yeah. I mean, how else do you order your food?
Yeah. Now, is that assembly right there? I don't know anything about assembly.
Oh, this?
Yeah, that.
Oh, this is actually part of a series of assignments we do in CSE 222. So we design data structures, ways of storing information efficiently. And to test the code that we're writing to do that, we need a front end. So I usually have people make a front end where they can put in simple one-line commands to say insert a 5 into this tree or delete a 7 or things like that.
Okay.
Actually, I have a whole chapter on parsing in that book that you got a copy of.
Okay, good.
All right, so back to Turing machines. So remember our setup with Turing machines. We have these tuples with a current state, a current symbol, a new state, a new symbol, and a motion, left or right. And we have this tape, and it's got symbols on it, and we have a series of tuples like this, and we have an initial state. We have an initial position of the tape, and when the system starts, it basically looks at the current initial state, the symbol under the read-write head, and it looks for a rule, which has that current state and that current symbol. And if it finds one, it will write a new symbol on the tape, it will go to a new state, and it will move either left or right. And then it starts over from the top, and it looks for something with the current state and the current symbol. And if it finds it, it writes a symbol, moves, goes to a new state. And it just keeps doing this. And so we started to play with these on Monday, just to get a feel for what these things might look like. So let me make a more interesting Turing machine, which I wish I had made ahead of time. So we're going to start in state S0. And make this one right. All right, so there's a Turing machine with 6 state transitions defined. And we want to see what this does. And I'm assuming that our tape is filled with blanks on both ends. And we have some sort of binary number in the middle. So let's put 0, 1, 0, 1, 0, 0 in the middle, surrounded by blanks. And I'm going to assume that we're starting sitting on top of that rightmost 0. And we're starting in state S0. Let me move this down a little. All right, so what is this machine going to do? What's the first thing it's going to do? It's going to go left, it's going to write a 0, right? We're in state 0, we've got a 0 for our current symbol. State 0 and a 0 means stay in state 0, write a 0, and move left. So we'll leave a 0 in here, and we'll move to the left. We're still in state 0, so it's going to do exactly the same thing. It's going to leave a 0 there. It's going to move to the left. And we're still going to be in state 0. Now we're in state 0 and there's a 1. What's going to happen?
Moves to state 1, puts a 0,
Let me make this a 1. I made a typo.
puts in a 1, moves to, changes to state 1, and moves to the left.
Okay, so it leaves that 1 there, changes to state 1, and moves to the left. Okay, now we're in state 1. What's the behavior?
It's got 3 possibilities.
Mm-hmm.
Looks for either a 0 or a 1 or a B.
Okay.
And, okay, so there's a 0, so it takes the third one down.
Okay, so there's a 0. It's going to stay in state 1. It's going to write a 1, and it's going to move left. Now there's a 1. It's going to stay in state 1, but it's going to write a 0 and move to the left. And again, we're in state 1. There's a 0. It's going to write a 1. Stay in state 1, move to the left. Now it's in state 1 and there's a blank. It's going to go to state 2. It's going to leave the blank and it's going to move to the right. But it's going to go to state 2. And now it's going to say we're in state 2 and there's a 1. And there's nothing in our set of tuples for state 2 with a 1. So the machine halts. So what did it do to our tape? We had the original number 010100, and that was replaced by the number 101100. That's the 2's complement. So if you've done Engineering 250, when we have a negative number, we complement all the bits and we add 1. Well, that's what this machine just did. Because if our original number is 010100 and we toggle all the bits, we get 101011 and we add 1, we get 101100. That's the 2's complement. So this is a Turing Machine program that will give you the 2's complement of a binary number. So it's actually something useful. Now to make that work, we needed to know that we were sitting over that rightmost digit to begin with. And as long as we know that, what does this program actually do? How did I come up with this? I've written it before, but I essentially wrote it from scratch just now. How did I come up with this? Well, the trick for doing 2's complement, if you don't want to do all of this, is if you have a 0, keep it. If you have a 1, keep it. Keep all these digits from right to left until you hit a 1. And then start complementing, beginning with the next bit after that. So these first 3 bits are all the same, but because we hit that 1, now the remaining bits are going to get toggled. That's exactly what this does. It says if you got a 0, write a 0. If you've got a 1, leave that as a 1, but now go into this new state S1. S0 is a state where we're moving over and we're just keeping our bits exactly as they are. S1 is the state where we want to start toggling the bits. So if you have a 0, write a 1. If you have a 1, write a 0. And when you get to the end of your string, you'll hit a blank. That's when we go ahead and we halt. And if you just have a bunch of zeros, so you're just moving over and writing zeros, and you hit the end of your string, you'll hit a blank and you'll exit there. And the 2's complement of 0 is 0, because that's minus 0. So you can start to, if you work with these enough, you can start to do some synthesis. You can start to think of behaviors that you want and figure out what are the sets of tuples that I would make to achieve that. And like I said, this only works if we're starting over the rightmost zero, but what if we're not? What if we're sitting somewhere in the middle of this number? Can we write a Turing Machine program that will move us over to that rightmost bit? Right, high level, what would be the steps? Given that all we can do is read, write, change states, and move left or right.
Just stay in one state and go to the right until you reach blank.
Mm-hmm. And then,
And start going left.
yeah, and then just go left. So wherever you are, just start moving to the right until you find a blank underneath you. And once you find that blank, now just move one spot to the left. And now you're sitting on top of that rightmost bit, and now you can use the code that we just wrote. So maybe our initial state is S10, and we'll say if there's a 0, let's stay in S10, let's write a 0, and let's go to the right. If you're in S10 and there's a 1, we'll stay in S10, write a 1, and go to the right. But if you're in S10 and there's a blank, let's go to S0, let's leave the blank, and move to the left. So now as long as S10 is our initial state, this will go until it gets to the blank, and that'll move left one spot, and then we go to S0, and we start our 2's complement program. Does that make sense? All right, here's a trickier one. What if you're not sitting over the number to begin with at all? What if you're sitting over one of these blanks? How can we seek the rightmost bit of our binary number?
Can you move to the right until you get a 0 or a 1, and then move to a different state, and then essentially do the same thing?
All right, so start moving to the right until we get over a digit, and then use this to move further to the right until we get to another blank, and then we're good to go. And if we happen to be sitting over one of these, we can simply move to the left till we get over a digit, and then either we're done at that point, or we could still use this S10 sequence. What if you don't know which side of the number you're on? Is there anything we can do?
Well, if you're at the left, if you're on the left, and you move one to the left and you find another B, you want to change direction and go back to the right,
Okay,
and vice versa.
and then,
Well, keep going until you hit a number.
okay, so this will totally work. So wherever you happen to be, no pun intended, right? Look to your left. If you find a digit, you're ready to go. If not, come back and look to your right. If you find a digit, good. If not, go back to your next thing to the left, and go back to the next one to the right, and the next one to the left, and the next one to the right, and keep doing this. And sooner or later, assuming there's a digit somewhere on this tape, you will encounter it. It's not efficient, but it'll work. But that's a really different kind of way of thinking about programming, right? So now we're like deep into the late night heavy music kind of mindset. But this was what was in people's brains, you know, in the 20s, the 30s, when we were sort of developing these ideas that led to all of this stuff. It was all very mathematical and sort of theoretical. And being able to do something at all is a whole lot better than not being able to do it. Period, right? Even if it seems really grossly inefficient. Yeah.
But it was all based on that, like, in World War II, were they feeding a single tape in that had this kind of arrangement? Is that where the motivation come from that? But then it's extending to a
So
much
the
more
World War
general
II stuff wasn't actually Turing machines, right? There were mechanical machines they were using to do some of the calculations they were doing to crack enigma. But it wasn't yet a sort of general purpose Turing machine, but Turing was involved in that work, and he was also building
Before
this
World War II.
idea. Yeah.
Before World War II.
Yeah.
But
And
it's
so
still
after
just-
the war, he started,
But it
developing
was
this
still a
stuff further.
single tape
Yeah,
type
yeah.
of
I
way he
believe
was
so.
thinking about.
Mm-hmm.
And then later on, it became applicable in more general terms.
Yeah. So Turing machine, the tape is basically the memory of our computer, right? And the difference is on the Turing machine, the tape is infinite, right? The set of states is finite, but the tape is infinite, whereas we have finite memory on our Turing machines. So you can do stuff with this. So there's a sample Turing machine program, and they've taken some liberties in here. So for example, they have comments, right? So normal Turing machine doesn't have comments, but they're letting you put comments in, which is useful, telling you what the initial state is and so on. And they have some wildcards and some other embellishments. So it's basically current state, current symbol, next symbol, tape movement, different order, right, left or right, and so on. But this is a program which will run. Here's the read-write head. Here's the contents of the initial tape, and there's blanks on the end. And we can run this, and it does that.
Happy face.
Happy face. And different input, sad face. So we can load example programs like binary addition. So what numbers should we add? Someone give me two, not too big numbers.
16 plus 32.
Okay, 16 plus 32. So 16 is that, and 32 is this. I'm going to make them both 6 bits because I think it wants that, I'm not sure. I'm going to load those in. And here's our program. So it's, 30 some steps, several states, and it should give us 48 in the end. And there's 48. So total number of steps, 115. It's not too bad. Binary multiplication. So let's try 5 times 7. So 5 times 7. And this is a little longer program. It's 123 steps. And so it's writing other symbols onto the tape, because the tape is its memory, right? It's the input and output, but it's also the only place that it can store information. There's 35, 32, 2, and 1. That's not bad. That was only 351 steps. And anything that you can do in C and Python and Java, you can do on a Turing machine. Right? Any algorithm that you can run in any other language, you can run on a Turing machine.
Try the primality test.
Yeah, this is a good one. So, so let's test the number 5 and see if it's prime. So this one is 220 some statements, 616 states. They're not using all the states. They're grouping them in chunks, right? Because you can call the states whatever you want. And there's some comments in here that will tell you what's going on, but it's still pretty hard to read this, right? Especially with things like should never happen. So let's go
The
ahead.
numbers on the left-hand side, in the white, are those referring to the numbers?
Those are state numbers.
Purple. So are the purple the state numbers? Or are the purple are just
The gray?
The number of lines of code?
The gray section here?
Yeah.
Yeah, that's just a line of code. So that's sequential. The first number here, that's a state number,
This
so
is
this is
the
state
state,
60.
Okay.
Move left, go to state 61. So we can run this. We're going to check to see if 5 is prime. This will take a while. So we can run it at full speed. Let's pause it and continue it. So that's a little faster. So 1,500 steps later, and that's prime. Okay, that's 5, so I had to divide by 2 and 3 basically. So let's try 31.
Almost 1,600 steps to get that done.
Yeah. So let's see if 31 is prime. I don't know if this will finish in a reasonable amount of time. We'll give it a minute or two. Otherwise, we'll leave it in the background.
Morfett, is that Morfett? Is that the guy that did this?
I don't know. So, I mean, how does this work? Well, you know, you need temporary variables. You need to know the number you're trying to divide by. Try dividing by 2 and 3 and maybe 4 and 5 or just the odd numbers or something. And you write that on the tape somewhere. That's your only memory, but you throw a symbol at the left of it to say, this is my temporary divisor that I'm going to try next. And you need to know the number that you're checking, which looks like the letter A is prefixing the number 31 that we're working with. And then you need to code the whole division process, which you can do with repeated subtraction. So keep subtracting until something becomes negative. Well, how do you subtract or add? Well, you do it digit by digit, and if there's a carry, you go to one state. If there's not a carry, you go to a different state, right? And it's a lot of parts and pieces and a lot of work, 33,000 steps and counting. But it will finish, and it should tell us that this is prime. So Turing machines were, like I said the other day, developed partially to study questions of computation. People were interested in what kinds of things can we compute, right? This was before computers and mechanical devices. Computer was a job title originally. Okay, it was like librarian or bookkeeper. Hey, it's prime. Cool, 45,000 steps. Let's try 33. Hopefully it'll find a factor pretty soon on that one. So computer was a job title, right? You could work as a computer and you sat at a desk with pencil and paper and you did computations all day. And when computers as we know them started to appear, they were always called electronic computers to differentiate from a real computer, which was a flesh and blood person. So before electronic computers were available, right, people were curious about what are the limits of what we can calculate. What can we say about our ability to solve problems? And to even ask questions like that, you need to have some sort of formalized notion of what it means to solve a problem, right? What we would call an algorithm today. And so a Turing machine was an early attempt by Alan Turing to formalize this idea of, you know, executing a sequence of steps. And it's nothing like what we do in C or assembly language today, but it was, you know, the approach that occurred to people at the time. And it turns out you can do anything with these that you could do in C or assembly language or anything else. But is there A? It's not prime. And that also took 35,000 steps. And it's fun to write this kind of stuff. Once you do it enough, you start to get the hang of it, and then it's like its own kind of fun. So what about things that a Turing machine cannot do? Are there any calculations that a Turing machine cannot perform? And this is an interesting question. This goes back to the turn of the century, early 1900s. Are there limits on computability? And so there's a famous question, which is nominally called the halting problem. And the halting problem is the following. Suppose you know all of the tuples that describe a program for a Turing machine, and you know what the initial input is. Okay, so you know the program and you know what's initially on the tape. And you know that this thing just keeps, moving the head, looking up new states, writing characters, reading characters, and so on. And it will keep going unless it encounters a transition to a state that doesn't exist. And in that case, the machine halts. So the halting problem asks the following question. Given a Turing machine program and the initial input, can you determine if the Turing machine eventually halts? Now, obviously, if you just start running this and you wait long enough and it halts, then you can say, yes, it will halt, okay? But that's not really a valid answer to the halting problem. The real question here is, by looking at the program and the input, can you tell in a finite amount of time whether the program's going to halt or not? And it's got to be in a finite amount of time. It might be 1 billion years. That would still be a solution to the problem. But it stops you from being able to say, well, I'm just going to run it until it halts, and if it halts, then I'll say, yes, it's going to halt. Because if you have a program that's going to loop forever, then you'll never get to the point where you can say, it's not going to halt. So you've got to be able to deliver an answer, yes or no, in some finite amount of time, but you can choose how big that finite amount of time is. And it's certainly possible to have machines right, that will just bounce back and, let me do a better one. Right, so this Turing program will run forever. If we start over the 0, we're in state 0 and there's a 0, it'll write a 0, go to state 1 and move left. State 1 and there's a 0, it'll move to state 0, write a 0 and move right. And it'll just bounce back and forth between state 0 and state 1, and the head will just move between those two digits. This will run forever, it will never halt. And I can look at this program and I can say, yes, that's going to halt. And I can look at this program and I can say, if this is my input, yes, this is going to halt. This will halt when it gets to the end here and it's written out the 2's complement. So this will halt, this will run forever. I can do that analysis on those two programs. The question is, given any Turing machine program and any initial input, can you always make that determination? And this was an open question for a while. And eventually it was shown that the halting problem is unsolvable. You cannot determine in a finite amount of time whether a program will halt or not. And the way that this was studied was to ask if you could write a program that would make this determination, in particular write a program on a Turing machine. But presumably, any program that you could write on anything, you could write on a Turing machine. So if you could write a C program that would tell you whether or not a C program halts, you would solve the halting problem. The claim is that you cannot write a program that, given a set of C code and a set of input you're going to feed into that, can tell you if it has an infinite loop or not. Right? And we know this from writing code. Sometimes our code should exit and it doesn't. Sometimes it should keep running and instead it seg faults and it halts. But the problem of determining that in general is unsolvable. So they say. Now, I have my own theories about this. I don't know if I believe this, because the most common proofs for this, I know counterexamples too. But it's considered to be unsolvable. And it's most likely unsolvable And let me tell you why. Suppose that you could solve this halting problem. Suppose that you could do this modified halting problem. You have this thing that we'll call Oracle. Okay, this magic program. And you can feed Oracle a C program and a set of inputs, and it will tell you in a finite amount of time whether or not that program is ever going to exit. Or it'll say it's going to loop forever. If you had such a program, think of the things you could do. You wrote programming assignment 2, it tests Goldbach's conjecture. Okay, instead of just going for 100 numbers, have it start working on all even numbers. And if it finds an even number that cannot be written as the sum of 2 primes, have the program exit. Now feed that program to your Oracle. And if your Oracle says, yes, this program is going to eventually exit, you know that Goldbach's conjecture is false. You know that eventually this C program will find an even number that can't be written as the sum of 2 primes. And if the Oracle says this program will never exit, now you know Goldbach's conjecture is true. So having such an Oracle that would solve the halting problem would let you swing it at all kinds of problems. And it's extremely unlikely that such an Oracle exists, just because you could tackle so many things. Is there an end to how many consecutive odd numbers are prime? Right? Well, write a program that just keeps looking for them, and turn that into something that halts. So halting problem is considered unsolvable. And you prove that by doing a diagonalization argument like we did with real numbers. You basically modify the Oracle so that if it announces a program is going to halt, it goes into an infinite loop, and if it announces a program will loop forever, it halts, and then you ask it to analyze itself. And if it decides that it's going to halt, it will then go into an infinite loop. And if it decides it's going to loop, it'll then halt. And so you kind of force it to lie to you in either case. But there's some twisty turny stuff in there. So halting problem. So that's part of why Turing machines were developed. So we've been talking about these kinds of systems, Turing machines. These are more strictly called deterministic Turing machines. It's deterministic because there's no randomness in here, right? If you know what your current state is and what your current input symbol is, you know exactly what's going to happen next. Because there'll be, 0 or 1 rules that match that state and input, and it will say, write this, go to that state, move in this direction. There's a variation of this called a non-deterministic Turing machine, or NDTM. Now, NDTMs don't exist, but they're really, really sweet devices. It's a Turing machine with a genie inside, and it's a friendly genie. It's a genie who helps you solve problems. And with a non-deterministic Turing machine, basically your movement from one state to another is not determined strictly by the program. There's a genie that will help you decide what state to go to next. Okay, so here's what this means. Suppose you have a yes-no question. You want to know if something is true or false. Sometimes it's really easy to prove something is false by finding a counterexample. So, can every even number be written as a sum of 2 primes? Well, we can write a loop that just starts trying, 6, 8, 10, 12, 14, and just keeps going and going. But if we had a genie, and we said, hey, what's a good number for me to try? And it would say, oh, try this number. And you try that number, and guess what? It can't be written as a sum of 2 primes. You're done, right? First number that you tried happened to be the one that gave you an answer. So non-deterministic Turing machine is a Turing machine with this genie inside. And the idea is, if we have this thing inside the machine that can direct our problem in an efficient way, we may be able to solve problems more quickly. So we can start looking at problems and say, how quickly can we solve them on a non-deterministic Turing machine? The answer is usually quicker than on a deterministic one. So search problems. How do we search for a number in an array? Well, I check the first entry, check the second entry, check the third entry, check the millionth entry. If you get all the way through the array and you haven't found your number, you can say it's not found. But if you get to the 419,000th, 282nd number, and there's where your thing was stored, you can say, yeah, it is in the array. Okay, so a non-deterministic Turing machine, if this genie knew which entry you should check first, right, you could find your number after a single operation. Because it would say, hey, check this entry first, and you check that, say, hey, there's my number. Okay, I'm done. Okay, so how do we apply this to interesting problems? So there's this traveling salesperson problem. One of the most famous problems in computer science. I'm making a mess. So picture a set of cities, and they're fully connected. And there's distances associated with each of these roads. And they might not be geometric distance. They might be like times, for example, that it takes to travel. So this might be 2 and 4 and 3 and 6 and 1 and 2 and 2 and 3 and so on and so forth. And the question of the traveling salesperson is, suppose you start at one city and your goal is to visit every city and return to your original. What's the path that lets you do this with the smallest total amount of distance or time, right? The smallest sum of the values on each of these links. And I mean, just traveling to the cities, you just go boing, 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 and you're back, right? But there's different lengths associated with this journey, right? So think of time, it makes more sense. You know, this is pretty far away, but there's a really fast path from here to here. So maybe you want to go from here to this one first. And then, you know, maybe this is only a distance of 1 also. So now you want to hop down to here. But maybe this one is, you know, 20 from here to here, and maybe it's 22 from there to there, and maybe it's 61 and it's 25, and once you're here, you got a really bad time because the distance is to everywhere else. So maybe you didn't want to take this one, maybe you just wanted to do this one, and then come across here, right? So traveling salesperson problem is, given such a set of information, what's the shortest path that starts at one point, visits every city, comes back? And we can do this pretty easily with some nested for loops because there's only so many possibilities. Let's say we're starting right here. Well, we have 1, 2, 3, 4, 5 cities that we can possibly go to. And once we've gone to one of these cities, where can we go next? Well, we have 1, 2, 3, 4, 5 cities we can choose from there. And wherever that leads us, we've got 5 cities we can go to, and so on. And if you don't want to go back to a city you just came from, then this would be, you know, 5 and then 4 and then 3 and then 2 and then 1. So for n cities, or maybe n plus 1 cities, you know, it's maybe n to the n or maybe n factorial possible ways that we can travel. And you simply calculate the total distance for each of those ways and you find the smallest. So it's an easy problem to solve. The challenge is trying to solve it efficiently. If you have 100 cities, 100 factorial is huge, right? It's not tractable. And some algorithms, if you have n pieces of data, we can solve them in n squared operations. So bubble sort, right, is an n squared. If you have 100 pieces of item, it takes you roughly 10,000 operations. If you have 1,000,000, it takes you roughly 1,000,000 squared, 1,000,000,000,000 operations. Some algorithms are nicer. Some of them are like log base 2 of n. So you have 1,000,000 pieces of data, it only takes you 20 operations to deal with it. It's a lot better than 1,000,000 or 1,000,000 squared. Some operations might be n to the 100th. That's a huge number. But these things are what we call polynomial time. Whereas n factorial is much bigger than any polynomial, right? Even though n to the 100th is huge, if n gets big enough, n factorial is going to be bigger than n to the 100th. N factorial will eventually be bigger than n to the billionth if n gets big enough. So fundamentally, this is much worse than this. So one of the holy grails for a while has been to try to find a polynomial time solution to Traveling Salesperson. Try to come up with some algorithm that does fundamentally better than n factorial or n to the n. Could be n to the 100th, could be n to the millionth, but something that's still a polynomial, right? A fixed power of n or better. Okay, that's $1 million standing prize if you can do that. And a lot of people try. And a lot of so-called amateur computer scientists try to come up with algorithms to do this. And nobody has succeeded. But we don't know that it's impossible. What we do know, though, is that if you can solve Traveling Salesperson in polynomial time, you can change the world. And here's why. When you study complexity theory, how much effort it takes to do certain things, we can talk about classes of problems or classes of algorithms. And we talk about a class called P. Class P problems are problems that can be solved in polynomial time. So bubble sort is a class P. Most of the sort methods we have are P-type problems because they're solvable in polynomial time. So P means solvable in poly time on a Turing machine. Kind of always talking about on a Turing machine.
Why P?
Polynomial.
Oh,
Yeah. All right. So, non-deterministic Turing machine with a genie. Basically, what a non-deterministic machine lets us do is it lets us ask yes/no questions. And so, if we added up the length of all of these links and we got some big number like, 743, we could ask this machine, is there a path through all the cities with a length less than 743? And it would probably say yes. And then we could say, is there a path with a length less than 742? And it would probably say yes. Now we can just ask yes/no questions. We can't say what's the shortest length path. But we can keep asking this question, how about 741? How about 740, 739? And eventually we'll say, is there a path with length less than 28? And it'll say yes. And we'll say, is there a path with length less than 27? And it'll say no. We've got our answer to our Traveling Salesperson problem. 28 is the shortest path. And the number of steps we had to perform was no worse than 743. right? It's no worse than the sum of, the lengths of all these edges, or the length of just one path that we can cut through here. So certainly in polynomial time, right, we can use this non-deterministic Turing machine to find the length of the shortest path through here. So there's a second class of problems called NP. And NP does not stand for not polynomial. It stands for solvable in polytime on a non-deterministic Turing machine. So it's the N from non-deterministic. All right, so P is solvable in polytime on a plain old Turing machine. NP is solvable in polytime on a fancy, super-duper, genie-enhanced Turing machine. And there's lots of problems that are NP that we don't know if they're P, like traveling salesperson. Okay, some NP problems are also called NP complete. So NP complete is a subset of NP problems. And here's the deal with an NP complete problem. Any NP complete problem, if you can find that that problem is also a P-type problem, then every NP complete problem is also P. If you can pick any one NP complete problem and solve it in polynomial time, then all NP complete problems are solvable in polynomial time. In other words, this is a class of problems that in some sense are similar enough to each other that solving one efficiently lets you solve all of them efficiently. And traveling salesperson is NP complete. So that's why if you can solve traveling salesperson in polynomial time, you solve a whole bunch of problems automatically in polynomial time, including problems that would be really interesting to be able to solve efficiently. There are also NP hard, which are so complex that even if you solve one of these, it doesn't say anything about other NP hard problems. But if you can solve one of these NP complete problems, it really tells you that NP and P are the same thing. And that's a sort of world-changing discovery. So here's some a useful list of NP complete problems, and these all have to do with things that are combinatoric or permutations in some way. So we didn't talk about graph theory. We're going to talk about that in 222. But things related to traveling through graphs, things like traveling salesperson, finding shortest distance. Traveling salesman decision problem, right? So that's what we're talking about. Partitioning sets, right? We were talking about partitions the other day. Partitioning problems. Knapsack problem we'll tackle in 222, trying to find the optimal way to put things in a bag with certain constraints on the items you can put in there. Trying to extract the maximum value. Looking for subsequences. Where are the good ones? Battleship, Mastermind, Free Cell, Minesweeper, Sudoku, Tetris, right? These are all NP complete. And on and on. There's a better list in here. So graph problems, solving two-variable quadratic polynomials over the integers. That's kind of cool. All right, Battleship Bejeweled, Bulls and Cows, Candy Crush Saga, Donkey Kong, and so on. Instant Insanity, I remember that one. Legend of Zelda, NP complete. Lemmings, Metroid. Pokemon. Right, so this is worth spending some time on, right? And Super Mario Brothers, of course. So this is in the realm of computation theory, right, and computability. And you can take courses in this, and it gets fairly abstract pretty quickly, but sometimes it ties right back into some very concrete things, like questions of computability and encryption and things such as that. All right, so again, none of that is on the exam, but I think it's good stuff to be aware of, and you'll bump into it in other courses, so I want you to have had a first exposure to it at least here. So I posted a study guide on Canvas already for the final. My suggestion would be take a look at that and then come with some questions on Friday. We can talk about whatever questions you have, otherwise I'll just go through the list and it'll be not very exciting, so it's better to have questions. But we'll talk about the final on Friday, and that'll pretty much do us for the lectures. So I will see you next time.